Okay, so welcome to another lecture on topology. In this particular lecture, we will look at the second countability axiom. We'll look at product topology on a countable product of sets. Now, we've already seen product topology on uh, x cross y, product of two sets, and we said we can extend that topology to any finite product. But now we'll extend it to a countable product. Of course, there is a general way you can define a product topology on any index product of sets, but I will not get to that because that the notation can be a little more tricky to deal with. I'll rather stick to countable product of sets. And finally, we'll prove theorem 30.2, which is essentially has four parts to it. That is, subspace of a first countable space is first countable, countable product of first countable space is first countable, subspace of second countable space is second countable, and countable product of second countable spaces is second countable. So very symmetric looking result, which talks about products and subspaces, and first and second countable sets, topological spaces. Yeah, these, whether you look at subspaces or whether you look at countable products, it goes through. First and second countable on a collection of sets implies automatically it goes on to its product as well as a countable product as it goes on to subspaces. Yes, so that's what we will do. So let's start. Okay, so we first start by defining what is meant by second countable. We've already seen first countable. We know that a space is first countable or satisfies first countability axiom at a point if it has a countable uh, basis at that point, or a countable collection of open sets at that point satisfying some condition. We've seen that. I won't go over it again. But now we are coming to second countable, and second countable is even more easier to define. A space X is said to be second countable if its topology has a countable basis, is said to satisfy be second countable or satisfy the second countability axiom if it has a countable basis for its topology. Meaning what? You had your space X, and suppose it has, we have seen the concept of basis, right, that can generate the topology tau that is there on X. If I can somehow find a basis for this topology which is countable, then we will say X is second countable. If I can find a basis for the topology which is a countable collection. Now, I'm not saying that every collection, every basis is countable. I'm saying there exists at least one basis which is countable. So if I can find at least one basis which is countable, then we will call the space second countable. By the way, given a topological space X, there are many possible bases that I might have for tau. In fact, tau itself is a basis for tau, and there might be many smaller sub collections which are bases, but some may be countable, some may not be countable. But even if you can find one such collection B which is countable, then space X is second countable. One immediate consequence of the definition is this note 1, which is second countable implies first countable, because what was first countable, you would have to look at a point X and check whether there are collection of open sets, a countable collection of open sets, such that if you give me any open set containing X, U is any neighborhood of this point X, then you have among these countable sets there is some B such that X belongs to B and contained inside U. That was first countable definition. Now we are saying that there is a basis itself here. For the topology only there is a basis which is countable. So it's very easy from a countable basis to get a countable basis at the point X. Why? You only among all the basis elements take those basis elements which contain the point X. So here's what I have done. Given this basis B for the topology on tau, take Bx, in fact you should use small x here, B small x, to be all those elements from this basis B which contain X, then it's very easy to see. First of all, it's a sub collection, it's only those which contain X. So if the whole collection is countable, sub collection will be countable, and it will satisfy this condition, because the fact that the whole collection B is a basis, given a open set U containing the point X, you have to have some B such that X belongs to B and is contained in U. But the fact that X belongs to B tells me it is there in Bx. So the condition of first countable, that condition is easily satisfied, because the moment you take your B, that B itself has to be in Bx because it contains the point X. So there is nothing here that's special. So second countable will always imply first countable. Okay, R is second countable. That's the next thing to see, is that the real line is second countable. And how do we conclude that R is second countable? Well, we look at this. So we are trying to establish R is second countable. We look at this collection of points which are of the form, we look at B, a basis. We've not yet proved it's a basis, but we look at this collection, rational intervals of the form P comma Q, where P and Q are rational numbers. So if you have the real line, I have already got it here, actually I don't have to draw it again. So you have the real line here. So in fact, I'll draw it outside and tell you what I mean. It's better that way. So what we are saying is, you look at intervals over here of the form. On the real line, you look at intervals of the form P comma Q, but ensure that the endpoints are rational numbers. It will not be difficult to actually show this collection is a basis, and it won't be difficult to show this is countable either. Why is this going to be countable? Because if you look at this collection B, it has a obvious relationship to a subset of Q cross, a bijective relationship to a subset of Q cross Q. In fact, there are more elements in Q cross Q than there are here. And if we know Q cross Q is countable, this has to be countable. Why do I say there are more elements in Q cross Q? Because more in the sense, you can find a 1 from here to here, you can find a 1 1 function, because you just take your P comma Q and take it to the other side to P cross Q. This map has to be obviously 1 1, because if you take two different points, two different intervals, and they're not points here, in B they are intervals. If you give me two different intervals, when do you say two intervals are different? At least one of the endpoints are different. So either if you take another one, P dash Q dash, either P dash is not equal to P or Q dash is not equal to Q, otherwise the interval is the same. Well, on the other side, it will go to P dash cross Q dash, and if one of the coordinates are not the same, the points in Q cross Q are not the same. So it's obvious that this function is 1 1. And so if I am having a 1 1 map from B to a countable set, B has to be countable. There is no other option for B. So it's very easy to, there will be multiple ways you can see why B has to be countable. But does it satisfy my requirements of basis? Well, what are the requirements of being a basis? If you, by now you should be very familiar with this. If I give you open set U in R, open set U containing X, so containing some point X, if I give you a open set U, I should be able to find a basis element inside U. So there should be that situation where X belongs to some basis element B coming from this collection B, and that is fully contained inside U. I should have this situation. How do I achieve that situation? This is clear from this picture over here. You see, because we already know one basis. We already know a basis for the topology on R. We know that all intervals of the form a comma b form a basis, right? All possible open intervals you take, that's a basis for the topology on R. So given an open set U and a point X, you know that there is an interval AB which contains, so you have the situation where X, where is that written? Yeah, you have this situation where X belongs to AB and that is fully contained inside U. Given an open set U in R containing point X, we know this happens. But I don't want any endpoints AB. I want a rational number comma rational number here. So in the picture you can see what we do. Well, X lies between A and B. So you have this situation where X lies between A and B. So A is strictly less than X and X is strictly less than B. But then we know the density of real line from analysis. You know that between two real numbers there is a rational number. So between, since A is strictly less than X, between A and X there is a rational P. Since X is strictly less than B, between X and B there is a rational number Q. That's enough. So now I have the situation where X will lie inside PQ and PQ lies inside AB and that lies inside U, so I am done. And I have already explained to you why this collection is countable. If you want, you can go over this. By the way, there is an error here in the writing. Please correct this. This is Q cross Q. Q cross Q. This collection is contained inside Q cross Q. Anyways, I think that's very simple. So I've already explained that to you. So it becomes very clear that this particular collection is a basis and it is countable. So it is, this R has a countable basis, but the original basis that we started with, all possible intervals a comma b, well, that is not countable. That is an uncountable collection. So R has the standard basis which is uncountable, but then we can get this new basis by taking only rational endpoints for the intervals. We can get a basis which is countable. So R is second countable. Okay, let's go next. That's just a cautionary note to you that even metric spaces need not be second countable, although your Euclidean spaces R, R2, R3, these are second countable. And going from R to R2, I hope you know how to extend it. So we have taken rational comma rational. For R2, you will have to take intervals, rectangles, right? For R2, you would have rectangles as basis, where it is some AB cross CD. I hope you remember this. There was AB, interval AB cross CD. Now I hope you know, if I want to get a rational collection, I only take intervals which are PQ, and maybe somewhere else you take, you take AB comma CD, where A, B, C and D are rational numbers. Then you will get a collection of rectangles such that these endpoints are rationals, and that I hope you can go ahead and check that that will be also a basis and a countable basis. And yeah, this can be then extended to any Rn. So Rn's will be second countable, but there are examples of metric spaces which are not second countable. For example, if you take R with the discrete metric, in fact you don't even have to take R, you can take any uncountable set. Because it has discrete metric, every singleton point will be open. So singleton X is open, and so there, if I had a basis, if I had a basis B, I have to have, this is open, this is like my U. Okay, given this U, I should be able to find a B such that X belongs to B and that is contained inside U. But there is only one choice for B then, and that is, there is only one choice for B, which is singleton X. So because singleton X is open, hence you have to have singleton X as a basis element. So every singleton point from R has to come in this basis. Given any basis for the discrete topology, it is true that that basis must contain singleton points. but then R is uncountable. So if every singleton point is there in a basis, meaning every set, if B has to have the singletons, singleton X, singleton Y, if these have to be there in B, and for every real number, then this collection has to have singletons every real number, and that's an uncountable collection. So any basis for R with the discrete topology has to be uncountable. That tells you that it can't be second countable. Another example that we have here is R with the finite complement topology. That cannot be second countable because it's not first countable. We've already shown it's not first countable, and we know anything that is second countable is automatically first countable. So that's another way of concluding that R with finite complement topology is not second countable, rather than going and trying to do it explicitly. I think explicitly also will be able to do it. Is n cross n in the dictionary order topology second countable? And this is a special set, n cross n. The only special points that come with n cross n are those at the bottom. If you draw it in R2, you will have this kind of a thing, right? I hope you see that, and that goes, this goes on up there, this goes on up, and this goes on. You can keep doing this in every direction. I hope you understand what I mean is, this is my point 1 cross 1, and this is 1 cross 2, and then 1 cross 3, and this is 2 cross 1, 2 cross 2, 2 cross 3, and so on. And in the dictionary order topology, now it's almost a discrete topology, that is singleton points like singleton 1 cross 3 is open. Why? Because singleton 1 cross 3 is the interval 1 cross 2 comma 1 cross 4. This is open. It's a basis element actually of the order topology. So all these singleton points are open, except these points, of course even 1 cross 1 is open because this is the least element, so you are allowed to have that. I hope you remember topology. 1 cross 1 is also open because 1 cross 1 can be written as closed interval 1 cross 1 comma 1 cross 2. This also is open. But then there are singletons which are not open, and which are those? That are these. 2 cross 1 is not going to be open, 3 cross 1, 4 cross 1, these are not going to be open because you need something more than this that you have, but then there is not, the points below are up here. So the moment you fix one of them, you are going to get infinitely many of them. So singleton 2 cross 1 is not open, but rather any open set which has singleton 2 cross 1 has infinitely many points of the form 1 cross n. Some point you will have to start here, and then all of those including 2 cross 1. So we have seen this topology before. I claim this is second countable. It's even obvious, then it's first countable. There was an exercise to show it as first countable. That you can do because although you don't have this singleton point open, what you have is at this point you have this collection. You can always, to show that n at the point, say you fix a n naught cross 1, at n naught cross 1 you look at this collection, you will have the collection of the form n naught minus 1, the previous one, cross any k comma n naught cross 2. You look at this, this is a interval in the order topology, and look at this for all k belonging to natural numbers. Then this collection actually is countable because you are taking over k belong to natural numbers. It's like saying take this point, all these points here, and go up to n naught cross 1. Then you start with the second one, cross 2 and go up all the way up to this point, then start at 3, go up all the way, take this point. Well, this is a basis at the point, this is a basis at the point n naught cross 1. That's very easy to establish. So this becomes first countable, and to get the countable basis, in fact, take all the, in fact, there is a easy exercise you can prove. If I have a countable set which is first countable, it is automatically second countable. I'll repeat. If I have a countable set, n cross n is countable. If I have a countable set which is first countable, then it is automatically second countable, because at every point you have a countable basis. You just take the union of them, take all of them together. Now it's a countable union of countable sets because the number of points is countable. So at every point there is a countable basis. So overall, if you take their union, you still get a countable set, and it's not difficult to show that's a basis. So you can prove that as an exercise. I can leave that to you as an exercise, that if I have a first countable space which as a collection of points the space is countable, then it's automatically second countable. So yeah, I will go next. Okay, so we come to the theorem that we actually need to prove. So I have already showed you this result. Okay, before that, I said that before starting with this theorem, I need to actually define that what is meant by product topology on a product topology on a countable product. So what do I mean countable product? My space X is a countable product of x1 cross x2 cross x3 cross so on. So my space X is a countable product of spaces, a set X. So what is a typical element in X is like a sequence. These are called sequence spaces also. So if I say X belongs to capital X, then X will be of the form x1 cross x2 comma x2 comma x3 dot 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 dot, where x1 comes from big X1, x2 comes from x2, x3 comes from x3, and so on. And it's not a finite product. It's so this X itself is like a sequence. In fact, not like a sequence. Every point in this capital X is a sequence whose components come. First component comes from x1, second from x2, third from x3, and so on. Okay, now I have such a space. If I have topologies given on x1, I have a topology on x1, I have a topology on x2, I have a topology on x3, and so on. I want to define a topology on X. Then there is a natural way, and we call that the product topology on this X. And how do we get that? We get that by defining the basis for the topology. Basis B for the product topology on X. And what does that look like, or how do I define that? Take B to be the collection U1 cross U2 cross some UN, it's not even fixed, cross xn plus 1. So after UN you have to take all the x's, xn plus 1, xn plus 2, and after that everything is an xn. Take all such collection of such sets. So this is a subset. Yeah, this is a subset of X, right? Meaning take all those sequences, or points in X look like sequences. Take only those sequences whose first component comes from U1, second component comes from U2, third component comes, nth component comes from UN, and the remaining you take, there is no restriction. So take these where UIs are open in Xi, and for all n belonging to natural numbers. So you don't even say, okay, I'm not doing it for a fixed n. So inside B there will be stuff like some U1 crossed X2 cross X3 and so on. There will be a some V1 cross V2 cross V3 cross, after that everything is X4 cross X5 and so on. So all these will be elements inside there. I'll leave that as an exercise for you. In fact, it's not an exercise, it's already done in the, just before we started with page 1, there were some pages in which this has been done, but I think it has been done in the general setting, not just countable product, any product. I will not do any product because it becomes complicated. So let me just stick to countable product. Go ahead and prove. So I will give you an exercise which I leave it to you to do. Exercise: prove that B satisfies requirements of a basis meaning given a point, those two conditions, and given intersection of two basis elements and a point in that intersection, there is a third basis element which contains the point and is contained in the intersection, all that kind of a thing. So this is actually a basis for a topology, and whatever topology it generates, that we call the product topology on this countable collection. I can tell you that I can just tell you a few things. For example, when you take R omega is defined to be R cross R cross R, the countable product of R. If I just take AB, A1, B1 cross A2, B2 intervals and keep doing this, keep taking all intervals, that's not open. If I just take a product of intervals, that's not open in the product topology. What I need is open. I can take open interval, open up to finitely many terms I can take open intervals, but after that I have to take R cross R cross R. Only then will I get open set. If I just take only open intervals and I don't stop at any stage, keep taking open interval. For example, why A1 B1, I can just take 1 cross 1 comma 2 cross 1 comma 2 cross 1 comma 2. That's a subset of R cross R cross R, but this is not open because inside this you cannot push in a basis element. Basis elements are of this form. In this case, basis element, after some stage you have to have everything as R. So you are only allowed to have finitely many terms which are not R. Remaining all terms have to be R. Finitely many of them can be open intervals, can be any open sets in fact in R. Okay, so I hope you have got a feel for the product topology on a countable set. Now we can go next. So this countable product of first countable spaces is first countable. When I say that, you will say, what do you mean countable? What is the topology on this countable product? Well, the topology on this countable product is the product topology that we just saw. Okay, the first thing is subspace of a first countable space is first countable. In fact, it is so simple that I don't think I will go to a fresh page and do is I can just show it to you right here in the notes. In fact, if you remember, what is first countable? A space is first countable if at a point, if you give me a point x, I can find a countable collection of neighborhoods of x such that if you then give me any other neighborhood u, I can always find one element of this countable collection which contains x, some b, and is fully contained inside u. I know x has this property. I want to show a subspace y also has this property. So take a let us take a point y in y. I want to show that there is a countable basis for the topology. But then y, if it belongs to y, y also is in x. X is first countable. So there is a countable collection b1, b2, b. This is a countable basis at the point y, but these sets are inside x. So b1, b2, b3, they are these open sets in the picture, but they are open sets in x, they are countable and they form a countable basis at this point y. But keep in mind, they are sets inside x. I want sets which are inside y and form a countable basis for the subspace topology. Well, there is one, the way we will go is quite obvious. We will take these and intersect with y. So we create this b tilde, a new collection, and you only take all these b1, b2, b3 and you intersect them with y. So they are clearly, since bi's, b1, b2, bn's are neighborhoods of the point y in x, these intersect with y will be neighborhoods of the point y of this small y in the set in the subspace y. So they are all open sets. We need to do, and they are countable. Why are they countable? Because b1, b2, this collection is countable. This is in bijection with that, except that you've intersected y, so this is countable. So it's quite clear this is countable. We only have to see that the condition is satisfied. And what is the condition? Given a open set in y which contains this small y. So given open set V in y containing small y. Given a open set V in y containing small y, I should be able to find an element of this collection satisfying my condition, and that has been done here. Very, very simple. So what we say is let V be a open set. So we take this V. V is inside, don't forget V is inside y. It contains small y. But because V is open in small y, we know, if you remember your subspace, there has to be some open set U. There has to be an open set U in x such that V is U intersection with y. So there exists a neighborhood U in x of the same point y such that V is U intersection y. But then U is open in y and then B is a countable collection. So there is a small b such that B is contained in U, then intersect on y on both sides, that B intersection y is in U intersection y, U intersection y is V, and this comes from B tilde. So intersect y comes from here, and so I have my condition satisfied. So it's just too simple for me to explain. I think you just read and understand this. So I won't get into that. So let's look at the more substantial part of this theorem. So the first part is just too simple. I've just done it. Let's do the second part of this particular. So I'll open a fresh page. Spaces is first countable. So let me take such spaces. So let xi's be first countable spaces. By the way, if you are following the notes, we are on page 11 and I take my x to be the product, in fact I will write it in the expanded form rather than, you can follow the notes, might have it in the, so x1 cross x2 cross so on, okay, the infinite product. Now what I need to do is I need to take a point x equal to say x1 x2, or I should say let x1 x2 dot 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 belong to x. I need to show that there is a countable basis at this point x. For that I will construct, so how will I construct this? For each I, so x1 is in capital X1, so there is a countable base collection of open sets in x1, capital X1 containing this point little x1. So for each I, there is a little xi is in capital Xi. So there exists countable collection, or let me say basis, countable basis bi at xi. You understand what that means because we already seen what it means to have a countable basis at a point. Now we construct our countable basis at this point x. We want the countable basis at x. For each x1 x2 xn there is a countable basis in capital X1 x2 xn. Now construct, so put your define b to be, define capital B to be equal to all what is that, sets of the form small not small b1 cross b2 dot 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 cross some bn, and then crossed with we'll just put x n plus 1 cross x n plus 2 and so on, it goes on, and the rest of them all are xn's, such that your bi's come from script bi, that is they come from the countable basis, comma, your n is any natural number, it's not fixed, this is not fixed, so you have to do this for all n kind of. Yeah, this collection, define this collection I claim will be countable basis at the point x. I will show that this is the countable basis at the point x. So first of all, why is this countable? Think of it this way. I will have inside here b1 cross x2 cross x3 so on, everything that is of this form where b1 belongs to the collection b1. b1 is just a what is that, coming from the countable basis b1 of x1. So this b1 is a subset of x1, right, it is inside this x1. Similarly, what I can have is I can have my another type of element in B, that is b1 coming from x1 cross b2 coming from x2, and then everything is x3 x4, they are all the whole set where b1 comes from b1 and b2 comes from script b, and I can keep doing this. Now I can do it b1 b2 b3, so I can have various kind of sets in script b in such a way that they are certain up to a certain nth stage you are having elements coming from BIs, these BIs, and after that everything is the whole set X. Now this of course is this, so there is one for n equal to 1, n equal to 2, n equal to 3, and so on. So this is going to be countable. I mean, at least the types are type 1, type 2, type 3, type 4, and for every n there is a type n. So they are kind of countable. Each one of these has how many elements? Well, all possible B1s I should take. So the type 1 has as many elements in this type 1 type as many as there are distinct B1s, because B1 comes from script B1, but that's countable. B1 is a countable basis, right? So of type 1 there are countable, of type 2 there are countable, of type 3 there are countable. In fact, this B is just a countable union of countable sets. So it's a countable collection. So B is countable because it is countable union of countable sets. Yes, whose elements themselves are sets. So these are sets, but they are all in one big countable collection. So it's quite clear that this B that we've constructed is countable. Now we have to show that it is actually going to form a basis at the point X, for which I need to take a open set containing this point X. So let I think I have used V equal to neighborhood open set containing X. But this is open in what topology? It's open in the product topology on this space, and we know that there is a basis for the product topology, U1 cross U2 cross UN, all open sets, and then everything X1 X2 Xn. So there has to be a basis element of that type. So there exists what is that? There exists for the I'll write it. There exists a set U1 cross U2 cross dot 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 cross UN. All these are open sets in U1 open in B1 in X1, U2 open in X2, UN open in Xn, crossed Xn plus 1 and so on. The rest of them are all Xn, such that your X belongs to this collection U1, not collection, this set U1 cross U2 cross dot dot cross UN, crossed with everything after that is Xn plus 1 and so on. And this is not only X belongs to this is contained inside V. But what is U1? U1 is open set UI. So Xi, X is X1, X2, Xn, Xi belongs to UI, and UI open in Xi, and we already have taken what was my BI. For each I there exists countable basis BI at Xi. So BI is a countable basis at Xi, and Xi belongs to an open set, so there has to be an element of that countable basis. So UI this implies there exists BI belonging to script BI such that Xi belongs to BI and BI is contained inside UI, and that will immediately show you that X, you can immediately realize that X will belong to B1 cross B2 cross dot 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 Bn. Each one of these are contained, B1 is contained in U1, B2 is contained in U2 and so on. Cross, of course, after that keep everything as Xn plus 1 cross and so on. and this is contained inside V. In fact, this is contained inside this set, and that is contained inside V. But anyways, it satisfies the condition of being a basis at the point X. So with that, you end up showing that not only is this is kind of what we did as B. So this collection that we started with B is countable, and it also is a countable, it's a basis at the point X. So we started with any point X and we found a countable basis at X. So X is first countable. The capital X is first countable. Okay, now the theorem, if you see, had, so we've done 1 and 2. Now there is a part 3 to it, right? A subspace of a second countable space is second countable. I have not done it, and I have not done it because if you have done this 2, it's almost exactly mimicking the same steps. So you have your y, you have your x. Second countable means X itself has a countable basis. How will you get a countable basis for Y? Well, you look at that countable basis and you take its intersection with Y. So you will get open sets in Y. If you have a basis and you intersect with a subspace, you get a basis for the subspace. We actually already proved that. So if you take a countable collection and each one of the elements you intersect with Y, you are going to get the number of elements in that collection. All of them you have intersected with Y. The number of elements in that collection will not increase. If at all, it will decrease, because many of them might just become null set. So if there is a countable collection and now you have a lesser collection, it's still going to be countable. So just take your countable basis for X, intersect all of the elements with Y, you get a countable basis for Y. That's as simple as that. And it's already been proved in one result that if you take a basis B for X and intersect all the elements with Y, you get a basis for Y. So it completely is even more simpler than 2 actually. This is very, very simple. Okay, so I hope you can do that, and try to mimic the same steps to get the fourth one, meaning what we just did as B, the same will work for the fourth one. It's just that, where is that? Yeah, here instead of having countable bases at every point, you will have countable basis for x1, countable basis for x2, countable. So you will just say let b1 be countable basis for x1, countable basis for x2, and so on, and then construct B in the similar manner. This B is exactly b1 cross b2 cross bn, where these come from the countable basis for each of the spaces, and the rest is just kept as x1, x2, xn. You should be able to show that itself, that is countable. We've just seen that's countable if each one of the sub collections is countable, and that in fact becomes a basis for what is that, the topology on X. I leave that to you. It is again very, very similar. So yeah, on page 12 you would have been asked to do those. Write down proofs for 3 and 4, which I leave to you. Write down short proofs to prove the particular case of 2 and 4. Show that if x and y are then x cross y. Okay. So exercise on page 12. I think page 12 will be here. I should put it up rather than read. Yeah, this is what I was reading. So I have asked you exercise 1, of course, just what I told you, and I've already explained how to do it. This particular, that's exactly proofs for 3 and 4. And there is another exercise over there asking you to write down shorter proofs if I only have to deal with x cross y. Like product, if x is first countable, y is first countable, prove that x cross y is first countable. Because very often if you look at the question papers of the exams and all, rather than ask the more lengthy proof, this is very often asked. Second count, very often people will, if you can do it for this, then you know how to extend it, kind of an logic. So you only ask the student, show if x is first countable, y is first countable, x cross y is first countable, or second countable. depending on what you want to ask. So I leave that as an exercise to you to use what we've done. We've proved it for all for the for x. In fact we proved it for the not only the finite case, we even proved it for the infinite countable case. But can you do it just for 2? I mean, obviously the fact that we've done it here, it means it holds here, but you can try writing down very short proofs for that. Okay, so that we complete what we need to do in this particular lecture. In the next lecture we'll look at separable and Lindelof spaces. So we'll stop here.